Hello, AP Calc. If you are in my class and watching this video as an assignment, please make sure that you take notes when I tell you to take notes. Any additional notes that you take would be appreciated on your end, so you don't have to watch the video again, but you can always access this video. I just really want the example problems down on your paper, okay? All right, that gives you a little bit of an out, but please watch the video and make sure you're understanding everything that goes along. We are in 4.2, dealing with area and summations. By watching this video and practicing a few examples, I'm hoping you will gain an understanding of the relationship between the area of a bounded region and an infinite summation. Now let's try to make sense of this. Area equals the limit as x approaches infinity of the summation as I goes from 1 to n of f of c sub I times delta x, which also happens to be equal to the integral from a to b of f of x dx. And that gets you into the Fundamental Theorem of Calculus, that n piece over here. Okay, let's first review the summation symbol. This is a Greek letter sigma, and it represents a summation in mathematics. Okay, the number on top, that n, I know I called it a number and it says a letter here, but it will represent a number as we go through perhaps. This n represents the number of terms in the summation if I equals 1. The I is the index of summation, not the imaginary I. You have to be careful here. I squared will not equal -1. We are not talking about complex numbers. We are just pretty much using the I. Well, this next statement says it here. It is pretty much a dummy variable and could be replaced with any other letter that isn't already being used to represent something else in the problem. So I think we're best to simply explain what's going on through an example. So let's take a peek at this next example. We have the summation as I goes from 1 to 6 of 2i. Since the I is starting at 1, I'm going to have 6 terms in my summation. So I set this up, repeating the 2i process with open parentheses in place of I. So I have 2 open parentheses, plus 2 open parentheses, plus 2 open parentheses, plus 2 open parentheses, plus 2 open parentheses, and then plus 2 open parentheses. Notice I have 6 terms that I'm adding up. I'm prepping for it. I'm going to start with a 1, and I'm going to put 1 here, 2 here, 3 here, 4 here, 5 here, and 6 here. I stop at the 6 because the 6 was my top number in this summation over here. So the summation answer is, of course, 42 to the problem, which I suppose could be boxed here. However, I just want to point out that since we did factor out that common multiple of 2, the summation could be rewritten with a 2 on the outside. Yikes, that was not a good idea. Let's back that up. With a 2 on the outside here, and the summation as I goes from 1 to 6 of just plain old I. That means that this I would be replaced with simply 1 plus 2 plus 3 plus 4 plus 5 plus 6. So this is a valid summation property. Let's look at our valid summation properties. We have 2 of them. Here are 2 properties. The first one says that the summation as I goes from 1 to n of k times a sub I is equal to k multiplied by the summation as I goes from 1 to n of just a sub I. Basically means that if you've got some constant multiple here, you can pretty much just pull it to the outside of your summation, just like we do when we take a derivative and an integral. Okay, k is the constant multiple, and constant multiples can be pulled to the outside of summations. Okay, the summation property number 2 says that the summation as I goes from 1 to n of 2 different things, a sub I plus or minus b sub I, is equal to the summation as I goes from 1 to n of the first thing plus or minus the summation as I goes from 1 to n of the second thing. You'll hear me say in class and on this video that the summation of a sum or difference is equal to the sum or difference of 2 summations. So you can break up summations, which is kind of cool. It's kind of like the distributive property, if you will. Okay, so moving on to summation formulas. We have a few summation formulas here. There's 3 of them. So several if you want to consider several, 3 or more. Okay, The first summation formula you should have seen before in pre-calculus and maybe even algebra 2 is the summation as I goes from 1 to n of any constant, c, is equal to that constant c times the number of terms you're going to have, so cn. And we're doing an example over here. So I'm looking at the summation as I goes from 1 to n of just 5, which means I'm going to have 4 terms because I'm starting at I equals 1. So I set myself up for 4 terms, 1, 2, 3, 4, and the only thing going in there is the 5 repeatedly. So that gives me 5 times 4 is 20, and that represents the summation formula over here. And that means we don't have to write this thing out anymore. We can just jump to the summation formula. If we see this question, let's back this up a little. If we see this question, we can just say that answer is 5 times 4 is 20, and we don't have to write out the summation anymore. Okay, the second summation formula is for the summation as I goes from 1 to n of just I. And that answer is n times n plus 1 divided by 2. Now let's see what that means. If I give you the summation as I starts at 1 and goes all the way to 8 of just I, it means I'm adding 8 terms. I'm starting with 1 and then 2, 3, 4, 5, 6, 7, 8. If I add those numbers up, I get 36. 36 is the answer to that summation problem, just like 20 was the answer up here. Got it 2 different ways. Okay, but instead I could use the formula, and I could just say, well, my n is 8, so I can plug an 8 into the formula. I can get 8 times the quantity of 8 plus 1, all divided by 2. That's 8 times 9, which is divided by 2. I canceled the 8 and the 4 here, 8 and the 2, and got a 4. So then 4 times 9 gave me 36. Same answer, using a formula, not writing out a bunch of terms. Which would be really nice if you had to write out a whole bunch of terms. You want some kind of a formula instead of doing something out by hand. The third formula here is dealing with the summation as I goes from 1 to n of I squared. And that formula is n times the quantity of n plus 1 times the quantity of n 2n plus 1 all over 6. So let's do an example here. I have a summation as I goes from 1 to 5. Let's get my marker back in here. As I goes from 1 to 5 of I squared. So I'm going to have 5 terms in my summation. So 1, 2, 3, 4, 5 terms in my summation. And I'm going to substitute the 1 in for the I, and then I'm going to substitute a 2 in for the I, and then a 3, and then a 4, and then a 5. And I do that right here. I have 1 squared, and then 2 squared, and then 3 squared, 4 squared, 5 squared. I add all those up, and I get an answer of 55. Good thing I didn't want the summation as I goes from 1 to 20. First off, my numbers would be huge, and I would have 20 numbers I'm adding up. Instead, I can just use this formula right here. And I can say, well, my formula says I'm going all the way up to 5, so my n is 5. So 5, I just substitute a 5 everywhere I see an n in my formula. So 5 times 5 plus 1 plus 2 times 5 plus 1, all divided by 6. You can work that out. You're going to get 55 as well for your answer. Okay, I'm going to back that up for a minute and get those circles off my formulas, so in case you want to look at them again. Very good. And I will box that 55 all over. Very good. So now we have a formula number 4 here for the summation as I goes from 1 to n of I cubed. You can see how the formulas work. I'm not asking you to understand where the formulas come from, just to be able to apply them. So here I'm asking you to give me the summation as I goes from 1 to 6 of I cubed. That means I can use the formula, or I can just work it all out. This one's kind of easy to work out. I simply have to add the cubes up from 1 to 6. So you can see I'm going to have 6 terms. 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, and 6 cubed. I add all these up and I end up getting a sum of 441. However, if I simply use a formula instead, just grab this formula, bring it down here, and substitute a 6 everywhere I see an n, it gives me 6 squared multiplied by 6 plus 1 quantity squared, all divided by 4. 6 squared is 36. 6 plus 1 is 7. Square that, you get 49 divided by 4. 4 goes into 4 once. 4 goes into 36 9 times. Now I'm multiplying 9 times 49. I still get 441. And it's much faster to use the formula than it is to actually work it all out. Okay, take a look at this example. We are going to calculate the summation as I goes from 1 to 10 of I multiplied by I squared plus 1. First thing we do is multiply that I through the binomial. We get I cubed plus I. And then we use our summation properties to break up this one summation. So we have two summations. So the summation of a sum becomes the sum of two different summations. We're looking at the summation as I goes from 1 to 10 of I cubed, plus the summation as I goes from 1 to 10 of I. I need to break up the summation because the I cubed is going to use one formula where the I uses a different formula. Okay, so the summation as I goes from 1 to 10 uses the formula for I cubed, which is n squared multiplied by n plus 1 over 4. So I'm putting a 10 into that formula here. And the summation formula as I goes from 1 to 10 of just I is n times n plus 1 divided by 2. So I'm putting the 10 in for the n in that formula. Okay? Hopefully that makes sense to you. You can always backtrack a little bit in the video and write down those formulas. And you simply work this out, simplify it down, clean it up, and you end up getting a summation of 3080, which is quite a big formula, quite a big summation for all those things. I wouldn't have wanted to add up all those 10 terms. So let's see here. Let's move on to another example. Evaluate the summation as I goes from 1 to n of I plus 1 divided by n squared for n equals 100, n equals 1000, and n equals 10,000. Now, because I'm going to do this summation for 3 different possible values, I want to simplify the summation before I do any substituting. I'm not going to work this thing out using n equals 100 as one problem and then do it all over again for n equals 1000 and then do it all over again for n equals 10,000. I am going to use my summation properties and formulas to break this question down into the least possible number of n's before I do any substituting. So let's do that. We are looking at the summation as I goes from 1 to n of I plus 1 divided by n squared. So we're going to bring that down here. Here's our question. And the first thing I want to do is bring any constant multiple to the outside. Because when we do a summation, we need to understand that it's the I that changes throughout the problem, not the n. The n gets substituted in, but n is supposed to represent a particular value. You're supposed to know whether n is going to be 100 or 1000 or 10,000, and for each particular summation, it will be a constant. So the 1 over n squared can get factored out. This n squared can get pulled to the outside. However, it's on the denominator, so we need to make sure it stays on a denominator. That's why we use 1 over n squared. And we're left with the summation as I goes from 1 to n of I plus 1. The 1 over n squared gets copied again, and then we're going to split the summation of sums into the sum of two different summations. Break the properties down. So we're going to call this the summation as I goes from 1 to n of I plus the summation as I goes from 1 to n of 1. Now we're going to use the formulas. When we use the formulas, the summation symbols will disappear. Okay? These properties just broke it down first. So the summation formula is going to allow us to replace the summation as I goes from 1 to n of I. It's going to allow us to replace this with this formula. And it's going to allow us to use this formula. This was the one where you had the summation as I goes from 1 to n of c to equal cn. So those are our properties up here on top, and then our summation formulas allow us to eliminate the summation symbol. And now it's just a matter of cleaning it up and simplifying down. Okay, so the 1 over n squared is going to stay to the outside. I'm going to multiply out the n times the n plus 1 and get n squared plus n, divided by 2 still. And then the formula here, I'm going to create a common denominator. You see how I have a 2 on this first fraction? I want a 2 on the second fraction, which means I'm going to multiply by 2 over 2, giving me 2n over n. Notice the 2's could cancel off and you'll be right back to 1n. All right, keep moving along here. Since I got a common denominator, I might as well put them together. That was the whole purpose of it. So my n squared comes down here, and I have an n added with 2n, giving me 3n. Now I'm going to take this 1 over n squared and I'm going to bring it back inside my brackets. I'm going to end up factoring an n off the top, getting me n times n plus 3. And on the denominator, I'm going to multiply these together, and I'm going to end up with 2n squared. Is that making good sense to you, I hope? All right, let's move on. 1n can divide off here, and an n can divide off there. I end up with n plus 3 divided by 2n. I'm going to break that up, even though I really could give an answer right here, but I'm going to break this up to write this with the fewest possible n's that I can possibly use. So this is like a polynomial over monomial. So I'm basically going to take n divided by 2n, and then I'm going to take 3 divided by 2n, and we're going to use two different fractions. And we're going to cancel the n's off like this, divide them out, and we end up with 1/2 plus 3 over 2n. Notice I only have one n value in this final answer. This is written with the fewest possible n's because I want the least amount of work when I go to substitute in. So the original question, the summation as I goes from 1 to n of I plus 1 over n squared, is mathematically equivalent to 1/2 plus 3 over 2n, regardless of what the n is. So now, let's let n equal 100. If n is equal to 100, then the summation as I goes from 1 to n, let's see, this n right here is going to equal 100, is going to simply be this formula over here with the 100 put in for n. If you use a calculator with this, you just use your common sense, you end up with 0.515. If n equals 1,000, you again take this formula, and now you're just going to bring it down here, and you're going to use this formula with 1,000 in for n right here, like you did 100, and the summation ends up giving you 0.5015. If you use 1,000, no, 10,000, I apologize. If you use 10,000, you're going to put a 10,000 into the formula, and your answer is going to be ending up with 0.50015. Now these answers are doing something, and I want to see if you can figure out what's happening as n gets bigger and bigger and bigger. As n increases, the sum decreases. I mean 0.5015 is less than 0.515. So the sum is definitely decreasing, but what do you notice? It's not going to 0. It's getting closer and closer and closer to 0.5. So let's just talk about this here for a minute. The limit as x approaches infinity here, summation as I goes, and you know what, that shouldn't have said x. So let's just back that up a minute, and let's erase that x right there, and let's get an n written in there. I will do that occasionally, mess that up, so I apologize. But it's the limit as n is approaching infinity, right? We want n to get bigger and bigger and bigger. N was 100, n was 1,000, n is 10,000, and I want to see what's happening as n gets bigger and bigger and bigger. So n is approaching infinity. Summation as I goes from 1 to n of I plus 1 over n is equal to the limit as n approaches infinity of this answer that we had when we evaluated with the least possible number of n's. So if I put n to infinity here, if I put an infinity in for n down here, won't this make this fraction here really, really, really small? So the bigger the denominator gets, the smaller the fraction gets. This gives me 1/2 plus 0, which is just 1/2 or 0.5. So as n gets bigger and bigger and bigger, the overall answer to this problem gets closer and closer to 0.5. All right, so wrap this all up. To evaluate the limit of a summation, you use your summation properties first, and then use your summation formulas. That will eliminate the summation symbol in your problem. Simplify your algebra to the fewest number of n's, to the fewest number of n's possible. Okay, and then you evaluate your limit. And we've done a lot with limits, so we should be pretty good on that. Okay, let's move on. Hey, you know, I want to mention to you here, the limit as n approaches infinity is really talking about foreign behavior. And this particular function of 3 over 2n, that function right there is bottom heavy. And when a function is bottom heavy, and you're talking about going to infinity, then that function is approaching y equals 0. So there's another really good reason why that's a 0 right there. All right. Moving on. This is where we come into some how does this get applied questions. To approximate the area, let me do this. To approximate the area of a region bounded by a positive function that is above the x-axis, x equals a and x equals b. Now these are vertical lines we're talking about. X equals something, those are vertical lines. We can divide the interval from a to b into equal subintervals, creating rectangles, and we add the areas of those rectangles up to give us an approximate area of the region. I know that sounds like a whole bunch to take in at once. So go ahead, pause the video, back it up, read it again, make sure you're understanding what it's saying, and then we will work through. I guess I can't continue to backspace. It'll only keep so many things in our memory here, I guess. All right, so we'll just highlight that sucker again. Good enough. The formula you know for the area of a rectangle is area equals base times height. For our purpose, we're going to use area equals height times base. I'd like the height to come first because that's represented by our function, and then our base is going to be on the end. The base of each rectangle depends on the length of the interval and the number of rectangles the interval is being divided by or being divided into. The height of each rectangle, just like always the height of any function, is determined by evaluating the function at different x values along the interval. That should be logical. For the purpose of this lesson, we will need the given function to be monotonic. We've discussed that word, monotonic. That means it's strictly or always increasing or always decreasing on the interval given AB. Okay, it's a lot of information right there. You can go back and reread it maybe after we do a couple of examples, but let's see what we have. We're going to talk about an upper sum. Upper sum is denoted with a capital S, open parentheses n, which the n is going to tell you how many subintervals you're using. And this is the summation as I goes from 1 to n of f of capital M sub I times delta x. We use a capital M sub I because we are doing an upper sum. And capital letters represent upper sums. Okay, make sure you get that. Let's use this formula to approximate the area of the region bounded by the increasing function f, x equals a, x equals b, and the x-axis as shown here. So I drew you a function that was increasing, and nowhere did I actually write f of x, so I will do that. There's my f of x. And basically I want to talk about starting at x equals a, stopping at x equals b, and finding the area bounded by the function x equals a, x equals b, and my x-axis. Okay? So that region is shaded in this problem. And I'm dividing this region up into 1, 2, 3, 4 rectangles. However, rectangles have equal heights and equal bases, so you can see the rectangles are poking over a little bit here, right? They got a little bit extra. So this is going to be an approximation. We're not going to get an exact area, we're going to get an approximation. So the area of the rectangles themselves is actually going to be more than the true area of the region, and that's because we've got this extra stuff poking over the curve. Okay? Delta x, which stands for the change of x, is the width of each rectangle. You see how this is noted down here, delta x. We can find delta x by taking the number of rectangles we have, n is the number of rectangles, and dividing that into the length of the region that we're talking about. So if we're going from a to b, then the length of that interval is b minus a. We take our b minus a and we divide by n. That's over here. b minus a divided by n gives us the delta x that we're looking for. And this formula is super, super important. You will use this repeatedly. And it turns into something really cool with our definite integral as well. So we're going to make sure you understand that delta x is representing the width of each particular rectangle in our summation. Okay, delta x is the width of each rectangle. We find the width of each rectangle by taking the length of the interval and dividing it by how many number of rectangles we want. Okay, or how many subintervals we want. That will be the same thing as the number of rectangles. Okay, So next here, although this figure shows the interval from A to B divided into 4 subintervals, this should say subintervals right here, but it says intervals, this process works for any number of subintervals. Okay? You know, I think I'm going to change that, if you don't mind. I am going to erase that 4, and I am going to put the 4 here, and put subintervals, just like that. Now it works really nice. So this interval is divided into 4 subintervals, and this process works even if we said 10 subintervals, or 100 subintervals, or 3 subintervals. It really doesn't matter how many subintervals. The process is going to work regardless. I'm just going to work it out with 4. Okay, so notice the height of the first rectangle is not f of a. We know that to get a height you have to evaluate the y coordinate, which means you got to plug an x value into the function itself. So the height of the first rectangle looks like it's about this high right here. The height of this first rectangle comes from evaluating this x value down here. So do you see this? This x value that I'm putting a dot on right here, when you put that into the function of f, I touched my pen wrong, and you put this x value into the function f, you get this height right here, which is the height of the first rectangle. It's a little bit higher than the rectangle should be. Okay, so notice the height of the rectangle is not f of a. The height of the first rectangle, which is called f of m sub 1, mon because it's the first rectangle, is the length of its right side. If we're looking for an upper sum of an increasing function, we got to go to the right. This is always true when calculating the upper sum approximation of an increasing function. If a function is increasing and you want an upper sum, you've got to use this value on the right. Not the value on the left, but the value on the right. And that's kind of important. Okay, moving along. Capital M sub 1 will equal a plus 1 delta x. I can write a 1 in here, if that makes any sense. But if I take my a value and I add one little delta x, the width of each rectangle, it'll bring me to the right side of the first rectangle, giving me a plus 1 delta x. So when I use m sub 1, capital M sub 1, and I plug it into the function itself, giving me f of m sub 1, this gives me the height of the first rectangle. If I add another delta x, it'll bring me over to the right side of the second rectangle, which means capital M sub 2 would be a plus 1 delta x plus another delta x, making 2 delta x. And if I take this value, a plus 2 delta x, which is known as capital M sub 2, and I substitute that into my function, that gives me the height of my second rectangle. And yes, the process continues. Keep adding another delta x over and over and over, and you get the height, you get the m value that you need to plug into the function in order to get the height of the next rectangle, and so on. Should be a dot, dot, dot here. So m sub n is equal to a sub n delta x, and if you take that value, plug it into the function, you get the height of the last rectangle, because we have n rectangles. So f of m sub n gives you the height of the last rectangle. All right, so let's get some kind of a formula built here. My delta x, you keep adding another delta x over and over and over. So as you see here, we are looking at a 1 first, and then a 2, and then a 3, and then a 4, and then a 5, all the way up to however many rectangles you have. So that's the thing that's changing. So we have m sub I equals a plus I delta x. That makes m sub I, when you put capital M sub I into the function of f, it gives you the height of whichever rectangle you're on. If this said m sub 2, then it would be the second rectangle. If it says m sub 5, it's the fifth rectangle. If it's m sub 1, it's the first rectangle. So f of m sub I gives you the height of the ith rectangle. All right, moving on. Let's have a little bit of an understanding there. Let's get back to our picture to gain a better understanding for our upper sum. Let's see here. The sum of the areas of all 4 rectangles equals the area of the first rectangle plus the area of the second rectangle, plus the area of the third rectangle. Oh, and I can see that is not right, is it? So I am going to put in here and plus the area of the second rectangle, and the third rectangle, and then the fourth rectangle. Don't know how that slipped by me before, but it did. We're going to add up all those areas of all those rectangles, and we'll get the sum. All right. So the sum of all four rectangles, height times base, height times base, height times base, and height times base. Notice we have four sums, so we are doing this 1, 2, 3, 4 times. And the rectangle's height keeps changing even though the base of each rectangle is always delta x. The height continues to change. So the height of the first rectangle is f of capital M sub 1. The height of the second rectangle we know is f of capital M sub 2. The height of the third rectangle is f of capital M sub 3. And the height of the fourth rectangle we know will be f of capital M sub 4. Do you see how the base is the same regardless? Because we were using equal subintervals. So the delta x represents the base of each one of the rectangles. So I'm doing this 4 times. This now gives me the summation as I goes from 1 to 4 of f of m sub I. See the I changes from 1 to 4, which would be m sub 1, m sub 2, m sub 3, and m sub 4. And the m itself is a plus I delta x. And that was from previous in our work. So hopefully you have that. Okay, now think about it. If the upper sum with 3 subintervals is 226 squared units, because we're talking area, and the upper sum with 10 subintervals is 180.36 squared units, what do you think would be true about the upper sum with 100 subintervals? Or the upper sum with 1,000 subintervals? Or the upper sum with 1,000,000 subintervals? Why so? What general statement can you make about this capital S sub n? Well, let's look. The upper sum with 3 subintervals was 226 units, squared units. And the upper sum with 10 is 180.36 squared units. The upper sum with 100 subintervals would be smaller than the upper sum with 10, because obviously as our n is getting bigger, our upper sum is getting smaller. Does that make sense? The more subintervals that we have, the smaller the area is going to get. And yet, at the same time, even though the upper sum with 100 subintervals will be smaller than the upper sum with 10 subintervals, the upper sum with 100 is still going to be an upper sum. So it will still be greater than the true area bounded by the curve, x equals your left limit, x equals your right limit, and the x-axis. So I did a little calculation here, and the upper sum with 100 subintervals turns into approximately 163.8036. You could challenge yourself to see if you can get that as well. So as you can tell, 163.8036, and that's approximately, is definitely less than 180.36. So, but we're still not smaller than the true area or equal to the true area either. So if we did 1,000 subintervals here for the upper sum with 1,000 subintervals, that would even get smaller than the upper sum with 100 subintervals. And I did a little math there, and I figured that out to be approximately 162.180036, and chances are there's still some decimals after that. So you can see that 162.180036 is indeed smaller than, less than 163.8036. Not by much though. The difference isn't as big as it was between 3 and 10 subintervals, but still are getting a smaller total area the more subintervals you're adding. And yet that is still an upper sum, so the upper sum is still greater than the true area. What would happen if we went to 1,000,000 subintervals? And yeah, you guessed it, I did that too. I ended up finding out that 1,000,000 subintervals would give me an approximation, I don't like that symbol, would give me an approximation of 162.00018, which is indeed smaller than what we had at 1,000. I told you that was 162.180036. And yet, of course, even if you use 1,000,000 subintervals, you're still greater than the true area because you are dealing with an upper sum. So as the number of subdivisions increases, the thinner each rectangle becomes. And this results in less area that's sticking out above the function or hanging over the top. Therefore, the upper sum gets closer and closer to the true or the actual exact area of the region bounded by the function and the x-axis on that interval. The more subintervals you have, the closer and closer your upper sum gets to the true area, the less overhang you're going to have. So let's take a peek. Although I'm not going to discuss the lower sum in as much detail, it should follow that the lower sum would have a formula like the upper sum did, except now instead of a capital S of n, I'm going to use a lowercase s of n. And then instead of a capital M sub I, I'm going to use a lowercase m sub I. But it works through the same thing. Okay, I'm not going to get too detailed here. Let me see, you can read that for yourself right there. Whoops. So what I did is I created a little chart for you to look at, dealing with an upper sum and a lower sum, depending upon if you have an increasing or decreasing function. Now what we did was an upper sum with an increasing function. We played around with this idea right here. Notice how you have some little extra pieces poking over the function. That's what is going to give you an upper sum. If we had a decreasing function, the formula for your m sub I changes because now we do want to start on the left-hand side of our rectangles. And I'm not really going to discuss any of that with you because really it doesn't matter. We'll see that in just a minute. But you see how we still have an overhang here of extra pieces on top? So you have extra pieces on top of your function. That's what results in you getting an upper sum because our approximation is above the true area. Okay? Let's see. Let's get that out of there so we can have a really nice picture. Okay, lower sum just means that the rectangles that we're going to form are going to be below the function itself, which leaves a little bit of a gap. So it means that our lower sum approximations wouldn't even reach the true sum. So this gives us an under approximation. All right, fact of the matter is though, whether you're going over or under, as long as you head towards an infinite number of subintervals here, as n approaches infinity, we have an infinite number of subintervals. And when we have an infinite number of subintervals, the overhang or the gap really is negligible. So you don't have to worry about it, regardless of whether you're going to use an upper sum or a lower sum. As the lower sum increases, I'm going to do this, as long as you have n going to infinity, the lower sum will get bigger and bigger and bigger until it gets really, really infinitely close to the true area. Or the upper sum decreases and gets smaller and smaller and smaller, still stays an upper sum, so it's getting closer and closer to the true area. Both of them actually approach the actual area of the region bounded by the function and the x-axis on that interval. So theoretically, it wouldn't matter whether you used a lower sum or an upper sum. And for this reason, we have a formula here that says the area itself, the actual area, is equal to the limit as n approaches infinity of the summation as I goes from 1 to n of f of no capital M sub I or lowercase m sub I anymore, but c sub I times delta x, where c sub I can either equal a plus I delta x or a plus the quantity of I minus 1 delta x, depending upon if you're looking for an upper sum or a lower sum of an increasing or a decreasing function. But as long as your n is going to infinity, both the upper sum and the lower sum of an increasing or decreasing function is going to approach the actual true area that's bounded by that region. So really, why would we use something complicated? Let's X this one out, and let's always just use the simple one, a plus I delta x. Okay, very good. We're going to use that simple one. Moving on, and if you're in my calculus class, I would expect you to copy these next couple of examples that we do down, and that will wrap up the video. So let's conclude this video with a couple of examples that pull all of this information together. First example. Use the limit process to find the area of the region bounded by f of x equals 3x minus 4, the x-axis, x equals 2, and x equals 5. I am giving you the function. I am giving you your interval between 2 and 5, and I want it bounded by the x-axis. Okay? And 3x minus 4, I hope everybody can agree that 3x minus 4 is definitely going to be an increasing function on the interval between 2 and 5. So we're up in quadrant 1 here. So let's just plug a 2 into that. Let's see, 3 times 2 is 6, minus 4 is 2. So we're going from the point 2, 2. And when you plug a 5 into this function, 3 times 5 is 15, minus 4 is 11. So we're going from 2 to 11, obviously the function's increasing. And since this function is monotonic, being a straight line, we know that this function is increasing everywhere on the interval that I gave you. All right, let's see how we work this out. We're going to use this formula for area equaling the limit as n approaches infinity as of the summation of I equals 1 to n of f of c sub I delta x. So this is our formula that's up there boxed in purple. Okay? We know that our a value is a 2. So here's my a as a 2. We know our b value is a 5 because we're on the interval between 2 and 5. I know that's written in highlighter, which kind of sucks, but is what it is. Okay, get rid of that. Okay, so our delta x is 5 minus 2 divided by n. We're letting n go to infinity. We're having an infinite number of subintervals, meaning an infinite number of rectangles, which means that the thickness of each rectangle is paper thin. Super infinitely thin. All right, here we go. The delta x gives us 3 over n. Yikes, didn't mean to do that. So let's get that back on the paper here. Delta x is 3 over n. Our c sub I is a plus I delta x. We're going to use the easiest formula possible. Our a is 2. Put in a 2 for the a. Our delta x we just figured out was 3 over n. You're going to substitute a 3 over n for your delta x. And you're going to write c sub I equals 2 plus 3i over n. That means that our formula can be rewritten now. And we will say f of 2 plus 3i over n. And all we're doing is taking this c sub I and putting it in here. And our delta x is 3 over n. And I suppose if you wanted to have nice, neat brackets around here, it's nice and neat. Could put those brackets up here too. Very good. Okay, so what is our function doing? Our function f takes 3, multiplies it by the input, and subtracts 4 because f of x is 3x minus 4. So this is like 3 times your oogie boogie minus 4. Okay, and we're going to put the 2 plus 3i over n as our input into the function. So you see 3 times something minus 4, and the 3 over n is right over here, which is going to get factored to the outside of that summation in just a moment. Now here we go. This 3 over n is now over here, 3 over n. That gets tucked in, by the way, between the limit statement and the summation statement. Don't put it to the outside of the limit statement because this limit statement is what's going to make that n get evaluated. So you leave that there. The summation as I goes from 1 to n, I'm simply taking this 3 and multiplying it by 2 to give me 6. 3 multiplies by 3i over n to give me 9i over n, and then minus 4. Simplify down as much as you can, clean it up. So 6 minus 4 gives me 2. I still have this limit as n approaches infinity of 3 over n. And now I have the summation as I goes from 1 to n of 2 plus 9i over n. I'm going to break up my summations using one of my properties here. So this gives me the summation as I goes from 1 to n of 2 plus, and this 9 over n, you see this? 9 over n comes out as a constant. The summation as I goes from 1 to n of I. And now I'm going to use my formula. This is a summation formula that allows me to get rid of the summation symbol. This is a summation formula. This was a summation property, okay? And the formula allows you to get rid of the summation. So back where we are, This is just going to give me the constant multiple formula here. So you take your constant, you copy it down. I don't like that. And then you multiply by n. So you just get 2n out of this deal. This 9 over n simply gets copied right here, 9 over n. And the formula for the summation as I goes from 1 to n of I is n times n squared plus 1 over 2. Okay, we're going to clean this up, make it look nice. 2 times n is simply 2n. And then notice here that this n can cancel with this n, and I can just be left with 9 times n plus 1 divided by 2. Okay, hopefully that makes good sense to everybody. And now I'm going to multiply that 3 over n back in my brackets. So it's going to help clean up a few n's here. So when I multiply 3 over n times 2n, my n's cancel off and I just get 6. When I multiply 3 times 9 times n plus 1, 3 times 9 gives me 27, n plus 1. And the n on the denominator here multiplies through by 2 and gives me 2n on the denominator here. Hopefully that makes sense. Alrighty. Now, sometimes I would make a common denominator here, but I think I'm just going to split this up and get to this answer a little bit faster. The limit as n approaches infinity of this summation can be the summation of the two limits. So we just have 6 by itself. Since there's no n here, we just get a 6 out of this deal. Here we go. And then this other thing over here, this 27 times n plus 1 over 2n. I can look at this and tell that the leading coefficient on my numerator is going to be a 27, but I multiplied it out for you just in case. So this gives you 27n plus 27 over 2n. Notice that the degree of my numerator is a 1, the degree of my denominator is a 1. So therefore, if I take the ratio of the leading coefficients, I'd find out my horizontal asymptote would be 27 over 2. What do horizontal asymptotes describe? Far end behavior. What are we looking for as n approaches infinity? We're looking for far end behavior. So this question is basically asking me what is the horizontal asymptote of the function 27n plus 27 divided by 2n. As n approaches infinity, I get 27 over 2. 27 over 2 is the same thing as 13.5. 13.5 plus 6 gives me a total area of 19.5. And this is the area itself that is bounded by the curve. The two x values that were given to you, x equals 2 and x equals 5, along with the x-axis. Okay, this is a true area. This is exactly it because we let our number of rectangles or our number of subdivisions go to infinity, which didn't matter then if I was using an upper or lower sum. This actually is the true area bounded by the function and the limits that I had. Okay, so let's take this another step and check this answer by sketching this region and calculating the exact area using one or more area formulas from geometry. And I'm hoping actually that you end up using the trapezoid area. Trapezoid area is, let me see, area equals the area of a trapezoid. Area equals 1/2 the height times the sum of the two different bases. Okay, we're going to use that as we move along. First off, let's graph this thing. We want y equals 3x minus 4 graphed between x equals 2 and x equals 5. So there it is. Notice I have 2 plugged into my formula, 3x minus 4. I have 5 plugged into my formula, 3x minus 4. I can tell I'm going from y equals 2 to y equals 11, so I'm definitely increasing. And this is my function. Doesn't matter how many subintervals I use, I'm just going to go for using my geometry formula for the area of a trapezoid. I know that some of you would take this area and say, okay, well, I have a little rectangle down here, and then I have a triangle, so I could find the area of the rectangle, find the area of the triangle, and add them up. And yes, you can do that as well. That would be using 2 different area formulas, which is fine. But I just want to practice using the area of a trapezoid. So this is definitely a trapezoid. By definition, a trapezoid is a quadrilateral with exactly one pair of opposite sides parallel. So we have our parallel sides over here when we talk about x equals 2. And we got the other parallel side over here with x equals 5. Those are my bases. So my bases have heights of 2 and 11, which is why over here we have 2 and 11 substituting in for my bases. The height of this trapezoid is the distance between the two bases. And the distance between x equals 2 and x equals 5 is a distance of 3. So it's kind of like b minus a. This is the height of my trapezoid is a 3. Alrighty, put all that together. You're taking 2 plus 11, you're getting 13. 13 times 3 is 39, divided by 2 is 19.5. That is the same area we had by using the limit definition formula up there. Okay, so this worked out really nice because this was a linear function and I could find the area using geometry to prove everything to you. But this whole process that I've played with you with is is applicable even if the function is not linear. It is applicable whether you go above or below the x-axis, all kinds of different things, increasing, decreasing. We can do a lot with it. All right, let's analyze the following limit formula to determine the equation for the function f of x and the interval from a to b. So here I am, I'm giving you the setup, and I am asking you, what function am I playing with? So this is a question here. And what is my interval from a to b? That's my question for you. All right, well, let's do this. First off, I know that what goes inside my brackets in here, I know that this whole thing in here is the f of c sub I, and I know that this thing over here on the end is my delta x. So this is probably the easiest thing on the end here to play with here, the fact that my delta x is 6 over n. So let's do that. My delta x equals 6 over n. Now I have a formula for delta x. The formula for my delta x is b minus a divided by n. And this is equal to 6 divided by n. Which means now that my b minus a has to equal 6. Alrighty. Let's take a peek here at my c sub I. Can you tell what got shoved into this function up here? Can you tell what this c sub I value is supposed to be represented by? What's the expression for c sub I? I'm hoping that you can. It's this thing in parentheses and this thing in parentheses. It's consistent. So this is, c sub I is supposed to be like a plus I delta x. And according to the formula up there, it's 4 plus 6i over n, which should make pretty good sense here if you think about it. You see this delta x right here gets multiplied by I, and what's getting multiplied by I here? 6 over n, which is exactly what we figured out already was our delta x, and that means that this 4 has got to be the a. A is 4. I take that a is 4, I bring it back over to the fact that b minus a has to equal 6, and I simply put a 4 in there. And that gives me the b value is a 10. I now know a, I now know b, and therefore I know my interval from a to b. B is 10. Therefore my interval from a to b is the interval from 4 to 10. I am finding the area of some function between x equals 4 and x equals 10. Now what is my function? That's a good question. The function itself should be noticeable right here, right through here. If you know you're substituting 4 plus 6i over n, you should be able to kind of mimic that function right above it. This is 8 times something squared minus 5 times something plus 2. And if I'm talking about a function of x, well then x itself has been replaced with the a plus I delta x. So you know your function. You definitely know your function. Should be 8x squared minus 5x plus 2. So let's wrap this up. F of x is equal to 8x squared minus 5x plus 2. And my interval from a to b is the interval from 4 to 10. That's what I asked, and that is the answer to the problem. So that should be something you could sit and work through again if you needed to. Okay? Alrighty. This was me earlier working that out and writing that answer, so you know what I think I will do is simply erase this, because I already have it. and it's gone. Okay. I think that's pretty much it, you guys. We've had an example where you had to work through everything the long way, using the limit as delta x approaches infinity. All of this where you had to create the formula. You see this? Here's the formula right here that we had, like in question 2, the example that we just got done looking over. So if I were to give you this information, would you be able to turn around and tell me what the function was? I hope so. Looks like it's 3x minus 4. Looks like my delta x is 3 over n. All of this works out nice. You should be able to go either way. If I give you a function and your limitations with your x-axis and your 2 vertical lines, you should be able to come up with your formula and evaluate. Additionally, if I give you the formula to evaluate, you should be able to tell me what the function is and that you're going from 4 to 10. And I'm going to throw one more little tidbit into this problem just so that we can see something really neat. The area bounded by the curve and the x-axis and your x equals 4 and your x equals 10 actually gets written as a summation problem. So you got that idea. It's also, let me get my pencil back here, this is also equal to the integral from a to b of my function with respect to x. So this dx kind of shows up as your delta x in your problem, which makes sense. Dx typically stands for the derivative of x, but dx could stand for delta x and make good sense. Let's just do this with our fundamental theorem of calculus. Okay, we learned that the other day, so we should be able to wrap this up. This is the area from a to b, and my a in this case, I'm going to actually use my number here, 4. I'm going to use my 10. The function itself is 8x squared minus 5x plus 2 with respect to x. And I'm going to integrate this and use the fundamental theorem of calculus to evaluate my answer. This gives me, copy the 8, integrate x squared as x cubed over 3, minus 5, you integrate the x as x squared over 2, I'm just using the simple power rule, plus 2x, and this is evaluated from 4 to 10. This is the fundamental theorem of calculus coming up right here, these two steps together. So this is equal to big bracket 8 over 3 times something cubed minus 5 over 2 times something squared plus 2 times x. Close your bracket, minus, let's do it again for our lower limit, 8 over 3 times something cubed minus 5 over 2 times something squared plus 2 times something. All right, what number goes in my first set of brackets everywhere? It's the upper limit up here, this 10. Oops, I don't like that. We'll just write 10 again. So a 10 goes in for x everywhere in your first set of brackets. And in your second set of brackets, your 4 goes in everywhere for x. And you should be able to figure that out, decide what that represents to you. Let's see what we get here. We have 8 over 3. If I cube 10, I get 1,000. Minus 5 over 2, and I square 10, I get 100. Plus 20, this stays in brackets. Minus 8 over 3. If I cube 4, I get 64. Minus 5 over 2. If I square 4, I get 16. Plus 8. I want to put this all together. I could grab a common denominator everywhere. I could go ahead and distribute my terms. I'm just going to do one more, clean me up kind of thing. 8 times 1,000 is 8,000 divided by 3 minus 2 can go into 100 50 times. So 5 times 50 is 250 plus 20. Keep that in brackets. Minus, unfortunately, 3 doesn't go into 84, so I'm not going to lose that 3. However, 64 times 8, let me see, 32, carry a 3, 512, minus, 2 goes into itself once, 2 goes into 16 8 times, so that's minus 40, and then plus 8. Clean this up again. I'm looking at 8,000 divided by 3. Now, negative 250, positive 20 gives me negative 230. Okay. that doesn't look nice, so I'm going to erase both of those and just get that looking nicer. Minus 512 divided by 3. Negative 40 plus 8 is negative 32. Now, I could take the time to simplify these and get common denominators everywhere, but I think I'm going to simply subtract here at this point. 8,000 divided by 3 minus 230 minus 512 divided by 3 plus 32. You must distribute that negative sign. Okay? Now I'm going to go to the side and I'm going to say, what's 8,000 take away 512? So it's 7,488, I do believe. 7,488 over 3 still. And I have a negative 230 with a positive 32. This is going to give me a negative 198. So minus 198. Now, I could hit this two different ways. I think what I'll do is I'll just multiply this 198 by 3 over 3. And that will build a common denominator for me. So 7488 divided by 3 minus, and we're going to take 198 and multiply by 3 on the side. 24, carry a 2. 27 plus 2 is 29, carry a 2. Gives me 594. I now have a common denominator, so I can take 7,488 and subtract 594. I know, I'm doing too much, aren't I? So here you have 4, here you have 9, here you have 8, and here you have 6. Double check that to make sure that works. I'm pretty sure it does. This is now 6,894 divided by 3. And yes, of course, I want to see what that is. 6,894 divided by 3. We're looking at 2, 2. This gives me 29. 2 times 9 is 27. 24. This gives me a perfect number? How is that possible? I guess it is. I say a perfect number, I mean an integer value of 2,298. And that ends up being the area bounded by my function at y equals x squared, 8x squared minus 5x plus 2 between 4 and 10. So I know this is weird, but we know that this is some kind of a quadratic, right? I hope you know. Quadratic with a leading coefficient of 8, so I'm definitely not drawing it to scale. Somewhere here we cross the x-axis higher than 2, so somewhere we're dealing with an x-axis down here, and we're going from 4 to 10, and we just found all this area. Okay? Now I don't know exactly how well I've drawn this picture. Obviously it's not too well, but this is what's happened. This is what we've done. We found the true area bounded by the curve itself, x equals 4, x equals 10, and the x-axis. And that area is 2,298. All right, you guys, I think we're finished. So I'm going to wrap this up by saying, Talon out.